Imagine a robot trying to escape a maze. Every second, it has to make a decision. Move north, south, east, or west. Some choices lead to rewards. Others lead to penalties. And sometimes, the robot doesn't even know exactly where its next move will take it. So how do we teach it to make the best decisions? That's exactly what reinforcement learning is designed to solve. It starts with the Markov Decision Process, or MDP. An MDP gives us a mathematical way to describe how the world works. It has 5 important parts: states, actions, transition probabilities, a discount factor, and rewards. The state describes where the system currently is. For a chess program, it could be the position of every piece. For a helicopter, it could describe its position, orientation, and velocity. Actions are what the system can do. Move a chess piece, or control the helicopter. But the world isn't always predictable. After taking an action, the robot might not end up exactly where it expected. That's why we use transition probabilities. They describe the probability of reaching different next states. Then there's the reward function. It tells the system what outcomes are good and what outcomes are bad. Reaching the goal could give a positive reward, while entering a dangerous square could give a negative reward. And there's one more important idea: the discount factor. A reward received now is usually more valuable than the same reward far in the future. The discount factor controls how much future rewards matter. So now we have a model of the world. But what are we actually trying to find? The goal is to choose actions over time, so that the expected total payoff is as large as possible. The result is called a policy. A policy maps states to actions. When the system reaches a state, the policy tells it what to do. But finding the best policy isn't always obvious. Imagine the robot has 2 routes. One is shorter, but dangerous. The other takes longer, but is safer. Which should it choose? The MDP lets us calculate the long-term consequences and determine which actions maximize the expected payoff. This leads to one of the central problems in reinforcement learning. How do we find the optimal policy? Instead of guessing action by action, we can evaluate how valuable each state is. A state is valuable if it gives us access to good rewards in the future. Once we know those values, we can determine which action is best. And this is where dynamic programming becomes powerful. Start with an estimate of each state's value. Then repeatedly update those estimates, using rewards and the values of the states that can come next. Each update becomes more informed by future consequences. Eventually, the values converge. And once we know the optimal values, we can choose the action that leads to the best expected outcome. That gives us the optimal policy. So the bigger picture is simple. An MDP describes the environment. The reward function tells us what we want. Transition probabilities describe how the world responds. The discount factor tells us how much we care about the future. And the policy tells the agent what to do. Together, these ideas form the foundation of reinforcement learning. But this is only the beginning, because now that we know how to represent the problem, the next question is, how do we efficiently find the best values and improve the policy without solving everything from scratch? That's where value iteration and policy iteration come in. And that's exactly what we'll explore in the next video.